If you've been following the Monday Morning Haskell blog for the last couple of weeks, you'll know that we've been making a small game and running a breadth-first search algorithm so that we can navigate a maze and then visualizing that with the gloss library. These articles are linked in the description if you haven't read them yet and want to catch up. But an integral part of this game was this world type, which stored all of the game's information and helped us to process updates to the game. This week, we're going to discuss the OpenAI Gym, and this is a framework that's widely used to teach people about AI algorithms and how to use machine learning techniques to improve their algorithms. It has this concept of an environment that's very similar to this world idea we used in Gloss. And it's worth comparing these concepts, and it's especially fun to consider how we can recreate this environment idea in Haskell. This is a somewhat novel area where type families can actually help us out. So in the rest of this video, we're going to see how that happens. If you want to see the code for this video, you should follow the GitHub links in the description below. Pretty much all the code for this specific video is in the environment module, and just as a heads up, I do make some mistakes in the code that I'm writing on the screen for this video, so that GitHub repository is going to be the source of truth if you want to see the final code. Let's recall our world type from last time. This type stores all the information, both mutable and immutable, about our game. It tells us the grid we are navigating, as well as the current location of the player, which can change. Our game then is largely defined by functions that operate on this world. We require a function to draw our world, a function to change the world based on user actions, and a function to let the world evolve naturally. And of course, we need to create our initial world in order to start the game off. Now let's compare that to some code from OpenAI Gym. Here's a Python snippet you can find on the OpenAI Gym website. Let's note how this environment is used. We can make and reset our environment. Resetting it produces an observation. The environment also has an action space, and this is the set of available actions that the user can do in the game. We can also use this step function to move our environment forward, and this produces a new observation, a reward, and a boolean indicating if we're done. And of course, we can also render the environment. Like the world type, an environment clearly stores all the information about a game, but we also have this subset of information that we refer to as an observation. This is, generally speaking, the information that a player of the game actually has access to, and it ought to be mutable. Next, we step the game forward by using one of the possible actions at a given point. This is a combination of the input handler and the update function from our gloss example. When we step forward, we usually impact the world with our action, but the world also goes through its own natural evolution. This produces the new observation from which we base our next action. We also see a reward as a result of each action. This is something unique to the environment. Rewards are very important in training any kind of algorithm using machine learning. It's how we tell our program what a good move is. And of course, it's also useful to be able to render or draw our environment, though this isn't strictly necessary for the game's logic. There's a distinct drawback of using Python, though. The types of several of our environment-related expressions above are unclear. What information exactly is stored in the environment? What does an action look like, or an observation? In very basic games, both the action and the observation can be simple integers, but it's tricky to make heads or tails of that without already knowing what is happening in the game. So let's consider what an environment with this kind of API would look like in Haskell. We're tempted, of course, to make this a specific type, but we don't have type-level inheritance in Haskell, and we'll want to create some kind of pattern that different games can inherit from. So it's actually better to make this a type class, and since our game will need to have different side effects, we'll make it a monadic type class. And this is where the fun begins. Each different game environment will have its types associated with it, corresponding to the environment state, an action, and an observation.
So we can use type family syntax to associate these types with the class variable m. We can use these types within our other class functions as well. For example, we should be able to produce the current observation. And given the current observation, we should be able to describe the available actions. And we should also be able to reset the environment. Finally, we need two more items. First, our step function. This takes an action as an input, and it produces a new observation, a reward, and a boolean indicating whether or not we are done. And I'll also go ahead to the top of the file and create a new type called reward, and this will just wrap a double value for us, just to distinguish that a little bit. Now, the last item will be a little more Haskell specific. This will be a run function. It will allow us to take an action in our monad combined with the environment state and turn it into a normal IO action that we can run elsewhere. So this is kind of like run state t or something like that from other monads. If we are interested in rendering our environment, we can make a new type class that inherits from our base class. It should also inherit from IO because any type of rendering will involve IO. So we also have monad IO as our constraint there. And renderEnv will just be the one function in this subclass. Using our environment class, we can now write some generic code that will work on any environment or any game. So let's write a couple of loop functions, one corresponding to each of these classes we've just written. The first will work on any environment, though it requires that we supply our own function to choose an action. This was really the brain of the game, which we'll get into more in next week's video. But essentially, we will choose our new action, we will step the environment forward by using that action, and this will produce our observation and reward and the done boolean. And if we are done, then we can return the observation and the reward. Otherwise, we just recursively call back into our game loop. And if we want to render our game each time, this is a very similar function. We're just going to add the separate constraint that our monad must be a renderable environment, and we'll just add the extra steps for rendering this environment in the middle of this do statement.
So there are a lot of similarities between these two systems, but clearly OpenAI Gym is a little more involved and detailed. But Haskell provides some interesting mechanisms for us to add more type clarity around our environments. Next week, we'll actually use this environment class and apply it to our simple breadth-first search example game. This will really get us started on the road to applying machine learning to this problem. So you won't want to miss out. Make sure to subscribe to Monday Morning Haskell so that you can stay up to date with all the latest news. There is another link for that in the video description, so make sure to sign up.